Welcome to the I Can't Sleep podcast, where I help you learn a little and sleep a lot. I'm your host, Benjamin Boster, and tonight let's fall asleep learning about the planet Mercury. Mercury is the first planet from the Sun. It is a rocky planet with a trace atmosphere. While it is the smallest and least massive planet of the solar system, its surface gravity is slightly higher than that of Mars. The surface of Mercury is similar to Earth's moon, heavily cratered, with an expansive rupee system generated from thrust faults and bright ray systems formed by ejecta. Its largest crater, Caloris Planitia, has a diameter of 1,550 kilometers, which is about one-third the diameter of the planet. Being the most inferior orbiting planet, it appears in Earth's sky, always close to the Sun, either as a morning star or an evening star. It stays most of the time the closest to all other planets, and is the planet with the highest delta V needed to travel to from all other planets of the solar system. Mercury's sidereal year, 88 Earth days, and sidereal day, 58.65 Earth days, are in a 3:2 ratio. This relationship is called spin-orbit resonance, and sidereal here means relative to the stars. Consequently, one solar day, sunrise to sunrise on Mercury, lasts for about 176 Earth days, twice the planet's sidereal year. This means that one side of Mercury will remain in sunlight for one Mercurian year of 88 Earth days, while during the next orbit, that side will be in darkness all the time until the next sunrise after another 88 Earth days. Above the planet's surface is an extremely tenuous exosphere and a faint magnetic field that is strong enough to deflect solar winds. Combined with its high orbital eccentricity, the planet's surface has widely varying sunlight intensity and temperature, with the equatorial regions ranging from negative 170 degrees Celsius at night to 420 degrees Celsius during sunlight. During the very small axial tilt, the planet's poles are permanently shadowed. This strongly suggests that water ice could be present in the craters. Like the other planets in the solar system, Mercury formed approximately 4.5 billion years ago. There are many competing hypotheses about Mercury's origins and development, some of which incorporate collision with planetesimals and rock vaporization. As of the early 2020s, many broad details of Mercury's geological history are still under investigation or pending data from space probes. Its mantle is highly homogeneous, which suggests that Mercury had a magma ocean early in its history, like the Moon. According to current models, Mercury may have a solid silicate crust and mantle overlaying a solid outer core, a deeper liquid core layer, and a solid inner core. Mercury is a classical planet, therefore observed throughout history and recognized as a planet or wandering star. In English, it is named after the ancient Roman god Mercurius, Mercury, god of commerce and communication, and the messenger of the gods. The first space probe reached Mercury on March 29, 1974, which was Mariner 10, and has been visited and explored by other probes. Historically, humans knew Mercury by different names, depending on whether it was an evening star or a morning star. By about 350 BC, the ancient Greeks had realized the two stars were one. They knew the planet as Stilbon, meaning twinkling, and Hermes for its fleeting motion, a name that is retained in modern Greek. The Romans named the planet after the swift-footed Roman messenger god Mercury, whom they equated with the Greek Hermes because it moves across the sky faster than any other planet, though some associated the planet with Apollo instead, as detailed by Pliny the Elder. The astronomical symbol for Mercury is a stylized version of Hermes's caduceus. A Christian cross was added in the 16th century. Mercury is one of 4 terrestrial planets in the solar system, which means it is a rocky body like Earth. It is the smallest planet in the solar system, with an equatorial radius of 2,439.7 kilometers. Mercury is also smaller, albeit more massive, than the largest natural satellites in the solar system, Ganymede and Titan. Mercury consists of approximately 70% metallic and 30% silicate material. It appears to have a solid silicate crust and mantle, overlying a solid metallic outer core layer, a deeper liquid core layer, and a solid inner core. The composition of the iron-rich core remains uncertain, but it likely contains nickel, silicon, and perhaps sulfur and carbon, plus trace amounts of other elements. The planet's density is the second highest in the solar system, at 5.427 grams per centimeter cubed, only slightly less than Earth's density of 5.515 grams per centimeter cubed. If the effect of gravitational compression were to be factored out from both planets, the materials of which Mercury is made would be denser than those of Earth, with an uncompressed density of 5.3 grams per centimeter cubed versus Earth's 4.4 grams per centimeter cubed. Mercury's density can be used to infer details of its inner structure. Although Earth's high density results appreciably from gravitational compression, particularly at the core, Mercury is much smaller, and its inner regions are not as compressed. Therefore, for it to have such a high density, its core must be large and rich in iron. The radius of Mercury's core is estimated to be 2,020 plus or minus 30 kilometers, based on interior models constrained to be consistent with a moment of inertia factor of 0.346 plus or minus 0.014. Hence, Mercury's core occupies about 57% of its volume. For Earth, this proportion is 17%. Research published in 2007 suggests that Mercury has a molten core. The mantle crust layer is in total 420 kilometers thick. Projections differ as to the size of the crust specifically. Data from the Mariner 10 and Messenger probes suggests a thickness of 35 kilometers, whereas an airy isostasy model suggests a thickness of 26 plus or minus 11 kilometers. One distinctive feature of Mercury's surface is the presence of numerous narrow ridges, extending up to several hundred kilometers in length. It is thought that these were formed as Mercury's core and mantle cooled and contracted at a time when the crust had already solidified. Mercury's core has a higher iron content than that of any other planet in the solar system, and several theories have been proposed to explain this. The most widely accepted theory is that Mercury originally had a metal-silicate ratio, similar to common chondrite meteorites, thought to be typical of the solar system's rocky matter, and a mass approximately 2.25 times its current mass. Early in the solar system's history, Mercury may have been struck by a planetesimal of approximately 1/6 Mercury's mass and several thousand kilometers across. The impact would have stripped away much of the original crust and mantle, leaving the core behind as a relatively major component. A similar process, known as the giant impact hypothesis, has been proposed to explain the formation of Earth's moon. Alternatively, Mercury may have formed from the solar nebula before the Sun's energy output had stabilized. It would initially have had twice its present mass, but as the protosun contracted, temperatures near Mercury could have been between 2500 and 3500 Kelvin, and possibly even as high as 10,000 Kelvin. Much of Mercury's surface rock could have been vaporized at such temperatures, forming an atmosphere of rock vapor that could have been carried away by the solar wind. A third hypothesis proposes that the solar nebula caused drag on the particles from which Mercury was accreting, which meant that lighter particles were lost from the accreting material and not gathered by Mercury. Each hypothesis predicts a different surface composition, and 2 space missions have been tasked with making observations of this composition. The first Messenger, which ended in 2015, found higher than expected potassium and sulfur levels on the surface, suggesting that the giant impact hypothesis and vaporization of the crust and mantle did not occur because said potassium and sulfur would have been driven off by the extreme heat of these events. Bepi Colombo, which will arrive at Mercury in 2025, We'll make observations to test these hypotheses. The findings so far would seem to favor the third hypothesis. However, further analysis of the data is needed. Mercury's surface is similar in appearance to that of the Moon, showing extensive mare-like plains and heavy cratering, indicating that it has been geologically inactive for billions of years. It is more heterogeneous than the surface of Mars or the Moon, both of which contain significant stretches of similar geology, such as maria and plateaus. Albedo features are areas of markedly different reflectivity, which include impact craters, the resulting ejecta, and ray systems. Larger albedo features correspond to higher reflectivity planes. Mercury has wrinkle ridges, dorsa, moon-like highlands, mountains, or montes, plains, escarpments, and valleys. The planet's mantle is chemically heterogeneous, suggesting the planet went through a magma ocean phase early in its history. Crystallization of minerals and convective overturn resulted in a layered, chemically heterogeneous crust with large-scale variations in chemical composition observed on the surface. The crust is low in iron, but high in sulfur, resulting from the stronger early chemically reducing conditions than is found on other terrestrial planets. The surface is dominated by iron-poor pyroxene and olivine, as represented by enstatite and forsterite, respectively, along with sodium-rich plagioclase and minerals of mixed magnesium, calcium, and iron sulfide. The less reflective regions of the crust are high in carbon, most likely in the form of graphite. Names for features on Mercury come from a variety of sources and are set according to the IAU planetary nomenclature system. Names coming from people are limited to the deceased. Craters are named for artists, musicians, painters, and authors who have made outstanding or fundamental contributions to their field. Ridges or dorsa are named for scientists who have contributed to the study of Mercury. Depressions or fossae are named for works of architecture. Montes are named for the word hot in a variety of languages. Plains or planitii are named for Mercury in various languages. Escarpments or rupees are named for ships of scientific expeditions. Valleys or vales are named for abandoned cities, towns, or settlements of antiquity. Mercury was heavily bombarded by comets and asteroids during and shortly following its formation 4.6 billion years ago, as well as during a possibly separate subsequent episode called the Late Heavy Bombardment that ended 3.8 billion years ago. Mercury received impacts over its entire surface during this period of intense crater formation, facilitated by the lack of any atmosphere to slow impactors down. During this time, Mercury was volcanically active. Basins were filled by magma, producing smooth plains similar to the maria found on the Moon. One of the most unusual craters is Apollodorus, or the spider, which hosts a series of radiating troughs extending outwards from its impact site. Craters on Mercury range in diameter from small bowl-shaped cavities to multi-ringed impact basins hundreds of kilometers across. They appear in all states of degradation, from relatively fresh rayed craters to highly degraded crater remnants. Mercurian craters differ subtly from lunar craters in that the area blanketed by their ejecta is much smaller, a consequence of Mercury's stronger surface gravity. According to International Astronomical Union rules, each new crater must be named after an artist who was famous for more than 50 years and dead for more than 3 years before the date the crater is named. The largest known crater is Caloris Planitia, or Caloris Basin, with a diameter of 1,550 kilometers. The impact that created the Caloris Basin was so powerful that it caused lava eruptions and left a concentric mountainous ring roughly 2 kilometers tall surrounding the impact crater. The floor of the Caloris Basin is filled with a geologically distinct flat plain, broken up by ridges and fractures in a roughly polygonal pattern. It is not clear whether they were volcanic lava flows induced by the impact or a large sheet of impact melt. At the antipode of the Caloris Basin is a large region of unusually hilly terrain, known as the Weird Terrain. One hypothesis for its origin is that shock waves generated during the Caloris impact traveled around Mercury, converging at the basin's antipode, 180 degrees away. The resulting high stresses fractured the surface. Alternatively, it has been suggested that this terrain formed as a result of the convergence of ejecta at this basin's antipode. Overall, 46 impact basins have been identified. A notable basin is the 400-kilometer-wide multi-ring Tolstoy Basin that has an ejecta blanket extending up to 500 kilometers from its rim, and a floor that has been filled by smooth plains materials. Beethoven Basin has a similar-sized ejecta blanket and a 625-kilometer diameter rim. Like the Moon, the surface of Mercury has likely incurred the effects of space weathering processes, including solar wind and micrometeorite impacts. There are 2 geologically distinct plains regions on Mercury. Gently rolling hilly plains in the regions between the craters are Mercury's oldest visible surfaces, predating the heavily cratered terrain. These intercrater plains appear to have obliterated many earlier craters and show a general paucity of smaller craters below, about 30 kilometers in diameter. Smooth plains are widespread, flat areas that fill depressions of various sizes and bear a strong resemblance to lunar maria. Unlike lunar maria, the smooth plains of Mercury have the same albedo as the older inter-crater plains. Despite a lack of unequivocally volcanic characteristics, the localization and rounded lobate shape of these plains strongly support volcanic origins. All the smooth plains of Mercury formed significantly later than the Caloris Basin, as evidenced by appreciably smaller crater densities than on the Caloris ejecta blanket. An unusual feature of Mercury's surface is the numerous compression folds, or rupees, that crisscross the plains. These exist on the Moon, but are much more prominent on Mercury. As Mercury's interior cooled, it contracted and its surface began to deform, creating wrinkle ridges and lobate scarps associated with thrust faults. The scarps can reach lengths of 1,000 kilometers and heights of 3 kilometers. These compressional features can be seen on top of other features, such as craters and smooth plains, indicating they are more recent. Mapping of the features has suggested a total shrinkage of Mercury's radius in the range of approximately 1 to 7 kilometers. Most activity along the major thrust systems probably ended about 3.6 to 3.7 billion years ago. Small-scale thrust fault scarps have been found, tens of meters in height, and with lengths in the range of a few kilometers, that appear to be less than 50 million years old, indicating that compression of the interior and consequent surface geological activity continue to be present. There is evidence for pyroclastic flows on Mercury from low-profile shield volcanoes. 51 pyroclastic deposits have been identified, where 90% of them are found within impact craters. A study of the degradation state of the impact craters that host pyroclastic deposits suggests that pyroclastic activity occurred on Mercury over a prolonged interval. A rimless depression inside the southwest rim of the Caloris Basin consists of at least 9 overlapping volcanic vents, each individually up to 8 kilometers in diameter. It is thus a compound volcano. The vent floors are at least 1 kilometer below their brinks, and they bear a closer resemblance to volcanic craters sculpted by explosive eruptions, or modified by collapse into void spaces created by magma withdrawal back down into a conduit. Scientists could not quantify the age of the volcanic complex system, but reported that it could be on the order of 1 billion years. The surface temperature of Mercury ranges from 100 to 700 Kelvin. It never rises above 180 Kelvin at the poles due to the absence of an atmosphere and a steep temperature gradient between the equator and the poles. At perihelion, the equatorial subsolar point is located at latitude 0 degrees west, or 180 degrees west, and it climbs to a temperature of about 700 Kelvin. During aphelion, this occurs at 90 degrees, or 270 degrees west, and reaches only 550 Kelvin. On the dark side of the planet, temperatures average 110 Kelvin. The intensity of sunlight on Mercury's surface ranges between 4.59 and 10.61 times the solar constant. Although daylight temperatures at the surface of Mercury are generally extremely high, observations strongly suggest that ice exists on Mercury. The floors of deep craters at the poles are never exposed to direct sunlight, and temperatures there remain below 102 Kelvin, far lower than the global average. This creates a cold trap where ice can accumulate. Water ice strongly reflects radar, and observations by the 70-meter Goldstone Solar System radar and the VLA in the early 1990s revealed that there are patches of high radar reflection near the poles. Although ice was not the only possible cause of these reflective regions, astronomers thought it to be the most likely explanation. The presence of water ice was confirmed using messenger images of craters at the North Pole. The icy crater regions are estimated to contain about 10 to the 14th or 10 to the 15th kilograms of ice, and may be covered by a layer of regolith that inhibits sublimation. By comparison, the Antarctic ice sheet on Earth has a mass of about 4 times 10 to the 18th kilograms, and Mars's south polar cap contains about 10 to the 16th kilograms of water. The origin of the ice on Mercury is not yet known, but the two most likely sources are from outgassing of water from the planet's interior and deposition by impacts of comets. Mercury is too small and hot for its gravity to retain any significant atmosphere over long periods of time. It does have a tenuous surface-bound exosphere at a surface pressure of less than approximately 0.5 nanopascals. It includes hydrogen, helium, oxygen, sodium, calcium, potassium, magnesium, silicon, and hydroxide, among others. This exosphere is not stable. Atoms are continuously lost and replenished from a variety of sources. Hydrogen atoms and helium atoms probably come from the solar wind, diffusing into Mercury's magnetosphere before later escaping back into space. The radioactive decay of elements within Mercury's crust is another source of helium, as well as sodium and potassium. Water vapor is present, released by a combination of processes such as comets striking its surface, sputtering, creating water out of hydrogen from the solar wind and oxygen from rock, and sublimation from reservoirs of water ice in the permanently shadowed polar craters.